In this video, we will talk about a topic called analysis of variance, or as it is often abbreviated, ANOVA. Specifically here, we're going to talk about what is called one-way analysis of variance. That means that we are going to look at one independent variable that is measured across multiple populations, specifically 3 or more. So we did learn how to do a hypothesis test for the value of a mean. We learned how to look at 2 samples and see if their means were different from each other. In this case, we're going to look at 3 or more populations. The nature of analysis of variance is that it's always going to start with the assumption that all of the means for all of the populations are equal. So every ANOVA test has the null hypothesis that the mean of the first population and the mean of the second population and the mean of the third population, etc., for all populations are the same. So it works on the assumption that all of the means are equal. The complement to this, then, is that at least one mean is different from the others. That's all it takes to violate the rule that all of them are equal, is that at least one is not the same. Now, it's possible multiple populations can have different means. That is a question for a different type of test. In this case, we are simply looking to see, are all of the means the same? Analysis of variance is an F-test, meaning we will be using the F distribution, as was used for comparing 2 variances or 2 standard deviations. This will again use the F-test, which has a simple test statistic. It is simply a fraction of 2 values. The values here are what is known as ms sub b and ms sub w. What these things are the mean variance between the samples, hence the sub b, and in the denominator, it is the mean variance within the samples. Other words that are used for these sometimes are instead of between samples, we may say the mean variance of the factor or treatment. And instead of the mean variance within samples, sometimes we say it's the mean error. These things do have some calculation involved with them. Before we get to that, though, this being an F-test, it has to have a degrees of freedom for the numerator and a degrees of freedom of the denominator. The degrees of freedom of the numerator is going to be equal to k minus 1, where k is equal to the number of samples. So if we are looking at 5 populations, a sample chosen from each of 5 populations means 5 samples. In that case, k would be 1, or k would be 5, and 5 minus 1 would be 4. The degrees of freedom of the denominator, however, is equal to big N minus k, where big N is the sum of the sample sizes. it will help to see these in an example, which we will do shortly. Now, ms sub b and ms sub w require several steps of calculation. First, we're going to need the mean of each sample and the variance of each sample. So we need x bar sub I and s squared sub I for each sample. We're going to need the mean and the variance of each sample. We're also going to need something known as the grand mean. The grand mean, which is denoted x with 2 bars on top of it, the grand mean is going to come from adding up all of the sample values from all of the samples and dividing by the total sum of all of the sample sizes. So rather than find the mean of each individual sample, the grand mean comes from the idea of what if we lumped it all into one big thing? Now, once we have the mean and variance of each sample and the grand mean, we can then calculate the sum of the squares between samples, SS sub b. And that is going to be the sum of each sample size times the squared deviation of its particular sample mean from the grand mean. So let's look at what that is for a second. The grand mean is taking all of the samples and treating them as one big sample. Each x bar sub I is unique to each individual sample. So what we're doing when we take x sub I bar minus the grand mean, x double bar, what we're doing there is we're saying how much did this particular sample deviate from the grand mean, which is all the samples put together. How much did this one sample deviate from all the samples put together? And then, as we often see with standard deviations, we square these things because sometimes some of them will be below and have negative deviations, and some of them will be above and have positive deviations. So to avoid all of those things kind of canceling out, we square each of them so that they always turn out positive after the squaring. So the idea here is that we're going to take the deviation of this particular sample from the whole big pooled samples, square it, and multiply it by the sample size. The idea of multiplying by the sample size is to account for how many individual values were in that sample. We saw this in Statistics 1 when we calculated standard deviation or mean of a frequency distribution. The idea was to do the calculation once for one thing and then multiply it by a frequency, in this case a sample size, to account for multiple values in that sample. So if the sample size was, say, 10, then rather than calculate 10 different square deviations, we do one square deviation and then multiply it by 10. And it's just a quicker way of getting that sum. We are then going to do the same thing for each of the samples and add all of those things together. Once we have that, ms sub b is going to be the value that we just got, the sum of the squares between samples, divided by the number of samples we have minus 1. So again, the minus 1 is relevant to the degrees of freedom, but essentially what we're doing here is we're calculating the sum of the squares between samples. We're saying if we have 5 samples, we're going to do this calculation 5 times and add them all together. And then here for the mean is going to be, the mean squares between samples is going to be basically the average from the sum of squares between samples. This is also sometimes written as SS sub b over the degrees of freedom of the numerator. To get ms sub w, we need to find the sum of the squares within the samples. Now, when we're talking about between the samples, we're supposed to look at how basically each sample lines up with each other sample. We do that using the grand mean as a way of saying, hey, how does this particular sample's mean measure up against all of them put together? But when we're doing the sum of squares within samples, we're not going to cross between samples. We're going to stay within one. So we're not going to see the grand mean involved here because each sum of squares for each sample is going to be done individually. So here we have the sum of n sub I minus 1 times s sub I squared. So we're going to take the variance of a sample times 1 less than the sample size for that sample. And then we're going to add them all together. The mean of the squares within the samples is going to be SS sub w divided by big N minus k, also known as the degrees of freedom of the denominator. So we're going to need to calculate the mean and variance for each sample. We're going to need the grand mean of the entire data set. We're going to need to calculate the deviation of each sample mean from the grand mean, square it and multiply it by its sample size, and then divide that sum by k minus 1. We're also going to have to take each sample's variance and multiply it by 1 less than that sample size. Add those together and then divide by big N minus k. This is certainly a great deal of work to do by hand. Analysis of variance is rarely done by hand. It is typically done using some computer program, a spreadsheet, or even your calculator has the capacity to do one-way analysis of variance. The last thing we might talk about here before getting into an example is that once we have all of these things, we often assemble them into a summary table where we have the variation between samples and the variation within each sample. For each of these, we need the sum of squares also known as SS, so that here we would put the value for SS sub B, and here we would put the value for SS sub W. We also need the degrees of freedom. The degrees of freedom between the samples is k minus 1. And the degrees of freedom within the samples is big N minus k. Once we have each of those things, we can then find the mean of the squares, ms, by taking the sum of squares divided by the degrees of freedom. And then lastly, we can get our test statistic by taking the mean of the squares between the samples over the mean of the squares within the sample. And that is the statistic that we need to do our hypothesis test. As usual, once we have that, the rest is easy. We can either use a critical value if we can find that in an F table, or in a more reliable way, we can use the p-value method. Following the rules of the F distribution, the mean squares between the samples will be bigger than the mean squares within the samples, thus resulting in a test statistic, an F test, bigger than 1. So much like the difference between two variances or two standard deviations, one-way ANOVA tests are always right-tailed, or rather I should say, they're always two-tailed, because at least one mean being different from the others means that you would have a not equal to. However, being as it is two-tailed, we will always be using the right tail, and we would just then have to double the area of that tail in the case of the two-tail test. Let's look at an example then. We'll keep it small so that the calculations don't get completely out of hand. A medical researcher wants to determine whether there is a difference in the mean length of time that it takes 3 types of pain relievers to provide relief from headache pain. So several headache sufferers are randomly selected and given one of the 3 medications. Each person records the time in minutes that it takes the medication to begin working, and the results are shown in the table. We're going to do the one-way analysis of variance here using a 0.01 significance level. Now, in order to speed up some things here, I'm going to give some of the values that we need here. What we need for each sample is we need its sample size, we need its mean, which I will give to you here as 14, and we need its variance, which I will also give to you as 6. For the second sample, we need its sample size, which is 5, its mean, which is 17, and its variance, which is 8.5. For the third sample, its sample size is 4. The third sample's mean is 16.5. And the third sample's variance is 7. We need each of these values at some point in our calculations. Now, while we're here, it might be a good idea to come up with the values that we need for the degrees of freedom. We have 3 samples, so k is equal to 3. Big N is equal to the sum of the sample sizes. How many total data values are there? We have 4 values in the first sample, 5 in the second, and 4 in the third, for a total of 13. The next thing we need is the grand mean. The grand mean, x double bar, is going to come from adding up all of the data values and dividing by the total number of data values there are among the 3 samples. Again, saving some time here. The grand mean is going to come out to be approximately 15.92. These things are all easy enough to calculate on your own. The mean of each sample, the variance of each sample, and the grand mean. And again, if we're using a spreadsheet program, these are also very easy to calculate. We are now ready to start filling in with the sum of squares between and the sum of squares within. The sum of squares between the samples comes from the sum of, for each sample, its sample size times the deviation of its sample mean from the grand mean squared. So for the first sample, its sample size was 4. The first sample's mean was 14 minus the grand mean of 15.92, and that needs to be squared. We then do that again for the second sample. The second sample, there were 5 data values. The second sample's mean was 17 minus the grand mean of 15.92 squared. And then for the third sample, that had 4 data values and a sample mean of 16.5 minus the grand mean of 15.92 squared. All told, this is going to come out to be approximately 21.92. That is our sum of squares between. We also now are going to need the sum of squares within the samples. This comes from the sum of the sample size minus 1 times the variation of that sample. So the first sample had size 4, so 4 minus 1, times the variation of the first sample, which is 6. The second sample was size 5, so we have 5 minus 1, times the variance of that sample, which is 8.5. The third sample had a size of 4, so 4 minus 1, times the variance of the third sample, which is 7. This sum gives us 73. So we are at the point now where we have all the pieces that we need in order to build this summary table. So we have the variance between the samples and the variance within the samples. We're going to start out with the sum of squares. So the sum of squares between the samples was 21.92. And the sum of squares within the samples was 73. We then have to do the degrees of freedom. The degrees of freedom are k minus 1. There are 3 samples minus 1, so the degrees of freedom between the samples is 2. For the degrees of freedom within the samples, we had a grand total of 13 data values minus 3 for the number of samples that there are, and that gives us a degrees of freedom of 10. For the mean squares, then, we take the sum of squares and divide it by the degrees of freedom, and that gives us about 10.96. Within the samples, we take the 73 divided by 10 and get 7.3. So with those values in mind, we can now calculate the test statistic. The test statistic will be the mean of the squares between the samples divided by the mean of the squares within the samples. So our test statistic will be 10.96 over 7.3. And that will give us a test statistic value of approximately 1.5. From here, everything else works exactly the same that it should be working from any other hypothesis test. We need to find now a p-value. Now again, this is going to be a two-tail test because the alternative hypothesis is always that one of the means is not equal to the others. At least one of the means is not equal to. That makes for a two-tail test. That being said, we're always going to find the area in the right tail which is actually quite large here. An f-value of 1.5 is not that far from 1. So the probability of having an f-value here that is greater than 1.501 is actually quite large. 0.2690, etc. So our p 2 times that will be our p-value. And even without the multiplication by 2, this is quite clearly much, much larger. Much, much larger than our alpha value of 0.01. As we saw with the difference between two variances, An F statistic that is close to 1 will have us failing to reject the null hypothesis. We would need an F value that is very much larger than 1 in order to reject the null hypothesis. This 1.5 is so close to 1 that it is a very, very, very far ways off from being extreme enough to reject the null hypothesis. So we will, based on this, we will fail to reject the null hypothesis. Now, the null hypothesis said that all of the means were equal. What we see here is that there is not enough evidence to say that they're not. There is not enough evidence to suggest the means are not equal. Now, that being said, looking back at the sample means were 14, 17, and 16.5 minutes, respectively. None of these values are all that far off from each other. In fact, none of them were therefore all that far off from the grand mean. These deviations here were small enough to keep the sum of the squares between the samples relatively small. Now, any one of them could be close to the grand mean. The fact that all three of them were close to the grand mean is what kept the sum of squares between means small. Even one sample being dramatically larger or dramatically smaller than the grand mean would cause there to be a larger value for the sum of squares between. A larger value for the sum of squares between would therefore suggest a larger numerator for our F statistic, therefore giving us a more extreme results. So are the means exactly equal? No. But they are close enough that we can't say that they're dramatically different. Again, the nature of hypothesis testing is not to say whether the claim is directly true or not. It's to say, is the evidence strong enough to counteract it? Or is the evidence weak enough that we can't say it's not true? The sample means are definitely not all exactly equal, but they're not so far enough off from each other to suggest that they are noticeably different. Let me put it this way. This is all about taking medication to relieve pain from a headache. If you're taking a pain reliever for a headache, is the difference between 14 minutes and 16.5 minutes and 17 minutes, is that enough of a difference for you to go, oh, I'm definitely taking this medication and I'm not taking that one? Really? They're all close enough to each other that they're not all that much different. They're not different enough for it to matter. And that's really what it comes down to. Now again, there are statistical programs, there are ways in Excel that can do all of the calculation of analysis of variance for you. As far as we are concerned, we should be able to do each of these calculations on our own if needed. That being said, it is a bit time consuming to get some of these, but as long as these bits of information are provided for you, then that saves a tremendous amount of the time. Now, admittedly, this can get much more complicated. The more samples we have, the more means we need to calculate, the more variances we need to calculate, the longer it will take to calculate the grand mean, but also everything in here will get longer. We had to do this 3 times, once for each sample. If there were 5 samples or 6 samples, we would have to do it 6 times. The same thing down here. So the more samples you get, the bigger this is going to end up being, the more involved this calculation will get. And this is one of the reasons why we use computers, we use spreadsheets and statistical programs to do a lot of this calculation, because it is time consuming. And none of the calculations themselves are particularly difficult. It's just time consuming. And that's exactly where computers come into play, to do a lot of those simple and time consuming, mundane calculations for us so that we can focus on the bigger picture.